Now, let's take what we've learned and apply it back to the train example. So here again is the platform, and we're in the frame of the platform where there's an observer, Om Prakash, and several of his friends, and they all have synchronized clocks, as you can clearly see. Now a train passes them, and on this train is O prime Prakash, his evil twin, shown with this pink circle over here, and Om Prakash is shown with the black circle over here. And O prime Prakash as well has several friends, and this train is now going past the platform at a speed of v by c, which is 0.6. Okay, so beta in the language that we've introduced is 0.6. So it's getting very near the speed of light, this train, and now we'll see what happens as the train passes. So the train will pass, and at some point O prime Prakash will come face to face with Om Prakash. Now remember that everyone on the train has synchronized clocks. However, as we've seen, simultaneity is relative when you take into account the fact that the speed of light must be the same for all inertial observers. So in particular, Om Prakash and his friends appear to see that their clocks are synchronized, but when they look inside the train and take a peek at the times on all these clocks, they will all appear to be out of synchronization with each other. So let's take a look inside the train and see what each observer would see when they look inside the train and see what the corresponding value of the train observer's clocks are. So what you see looks something like this. So we've chosen the origin in time for the train observer so that Om prime Prakash's clock coincides with Om Prakash's clock at the moment that they pass each other, which is at t is equal to 0 seconds. But what you can see is that clocks which are to the right, that is the ones which are along the direction of motion, appear to have times which are further and further behind compared to the time shown on Om Prakash's clock, or equivalently all the ground observers' clocks. Whereas if you go to the left, which is further behind in the direction of motion of the train, these clocks appear to be further ahead in time. That is, these clocks appear to be dialed towards a future time. So this is what we mean by the relativity of simultaneity. That is, what appears to be a simultaneous instant of, let's say, Om Prakash and O prime Prakash meeting face to face is not a simultaneous instant. This time registers as a time of 0.07 seconds on all the train clocks observers. They will agree that at 0.07 seconds on their synchronized clocks, O prime Prakash came face to face with Om Prakash. But they will also say that at a time of minus 5.18 seconds, that is before O prime Prakash came face to face with Om Prakash, this orange observer on the train came face to face with this orange observer on the platform. Whereas for the platform observers, those two events of Om Prakash meeting O prime Prakash and this orange observer meeting this orange observer, those appear to be simultaneous events. And one of the implications that we've seen of the relativity of simultaneity and of these special relativity transformations is that the moving clocks appear to be out of synchronization as compared to the ground clocks. That is, there's a phase difference in the dial settings for these clocks. Now, we also saw a second implication for the special relativity transformations, which is that although all these clocks appear to be out of sync, or that is that they have a phase difference compared to the ground clocks, they will all tick at exactly the same rate. However, that rate of ticking of all these clocks will appear to be slower than the rate of ticking of the ground clocks. To see this, let's watch what happens to Om Prime Prakash's clock and Om Prakash's clock after some amount of time. And let's compare that to what happens, let's say, let's look at this blue clock over here, which shows a time currently of 4.57 seconds, which is in advance of 0.08 seconds. Okay, so I'm just going to play this movie forward and let's see what happens. Okay, so the first thing that you see is that if I look at all the ground observers, obviously the same amount of time has ticked for them. All their clocks appear to be synchronized with each other since we're in the frame of the ground observers. Now, if you ask how much time has passed for a particular clock on the train, for example, O Prime Prakash's clock, you'd see that only 4.1 seconds have passed since the instant that we started looking at this. All right, which is less time than has passed for any of the ground observers. But if you also look at this blue clock over here, you see that the time on this registers 8.67 seconds, which is also 4.1 seconds have ticked on this clock since we last looked at it. Which means that all these clocks are appearing to tick at the same rate, that is, the same amount of time has passed on each of these clocks of 4.1 seconds, which is a time which is smaller than the time measured by the ground observers. So these clocks continue to appear out of phase with each other, but they are all ticking at exactly the same rate, although that rate is slower than the rate at which the ground observers' clock are ticking. So that is to say that time appears to be passing more slowly for observers on the train. This phenomena is called time dilation. Now, let's look at the phenomena of length contraction. So, according to the ground observer, when they look at the separation between the friends on the train appear to be separated by a distance of 1 meter, which is the same as the separation of the ground observers. However, we know now from our study of special relativity transformations that moving rods, that is, let's say the moving length of a train compartment, which is, let's say, the distance between these two friends, would appear to be shorter as seen by the ground observers. What that means is, in the rest frame of the train, the separation between these two friends should actually be larger than 1 meter. By a similar token, the rest frame distance between these two friends on the ground, Om Prakash and his friend over here, is 1 meter in their rest frame. However, the train observers should perceive that the distance between Om Prakash and his friends is less than 1 meter, because this length would appear to be contracted according to the observers on the train. So, to recap, if we go into the frame of the train, we would expect to see that the observers on the train see a larger separation between each other, and they see a smaller separation between the friends on the platform. So to see this, let's change perspective and go into the rest frame of the train observers. So now we're in the rest frame of observer O prime, that is the train rest frame. And you can see the first thing is that all the clocks on the train are synchronized. And the spacing between the observers on the train is actually slightly, this is a distance of 1 meter, and you can see that the spacing between the train observers is actually larger than 1 meter. And when they look at the platform firstly appears to be moving to the left at the same speed, beta is 0.6, but in the opposite direction. And the second thing is that the observers on the platform, this is Om Prakash and this is his friend, the spacing between Om Prakash and his friends is smaller than 1 meter because of length contraction. Now let's fast forward to the time where Om Prakash and O prime Prakash come face to face according to the train observers. And now let's imagine that the observers on the train look outside and take a look at the clocks of the people standing on the platform. So Om prime Prakash looks at Om Prakash's clock, and this is the instant where they decide to set their clocks to t is equal to 0. And since all the clocks on the train are synchronized, they can all agree on what that instant t prime is equal to 0 is according to all the train observers. So now if we look at the friends on the platform and what their times are, what we would see is something like this. Once again, we see that in the direction of motion, that is, Om Prakash and his friends appear to be moving to the left. In the direction of motion, the clocks on the platform appear to have a phase lag, that is, they appear to be behind in time. And the clocks opposite the direction of motion appear to be further and further ahead in time, that is, their times are ahead of Om Prakash's clock. Also, if we were now to observe the rate at which all these clocks tick, these clocks would appear to tick slower than the clocks on the train are ticking. That is, when the train observers look at any one of these clocks and keep track of the rate at which they're ticking, they will appear to tick more slowly. For example, let's take a look at Om Prakash's clock after some amount of time. So after a time of 5.2 seconds has passed for all the train observers, what they see is that only a time of 4.16 seconds has passed for the clocks on the ground. And this is true for every single clock on the ground. They all tick at the same rate. That rate just appears to be slower. So this is the phenomena of time dilation once again. And once again, the moving clocks, as seen now in the rest frame of O prime Prakash, appear to be ticking slower. Or in other words, time appears to pass more slowly for the moving clocks, or the moving, the apparently moving platform observers. Let's take a look at what we've learned and compare it to the standard expectation of Galilean relativity. So in Galilean relativity, if we were to compare the clocks on the train with the clocks on the ground by each observer looking inside, what we would see is all the clocks on the train appear to be perfectly in sync with each other, and these clocks appear to tick at exactly the same rate as the clocks on the ground. So let's see how that would work. So the first thing that you see is all these clocks register the same time. That is, there's no synchronization lag. You look inside the train, every single clock reads the same value. And not only that, as we will see, let's play this forward in time, you'll see that these clocks keep exact pace with the ground observers' clocks. So if I freeze this at the instant where O prime Prakash and Om Prakash cross each other, you see that all the clocks are in sync. So the clocks appear to be in sync and time ticks at exactly the same rate. Now, moreover, if we go into the rest frame of O prime Prakash, the spacing between any two observers on the train, which is 1 meter apparently according to the ground observer Om Prakash, that length will still be the same in the rest frame of O prime Prakash. And O prime Prakash will also perceive the length between the observers on the platform to also be 1 meter, which would be completely unchanged. So if we switch perspective now to O prime Prakash's rest frame and we play this movie forward, what we would see is the ground or the platform appears to be moving to the left, and all the observers on the ground have the same spacing of 1 meter. The observers on the train have the same spacing of 1 meter, again in the rest frame of O prime Prakash. The clocks on the ground appear to be in sync, and they all appear to be ticking at the same rate as the clocks on the train. However, the crucial difference between Galilean relativity and special relativity is what happens to the speed of light. Let's try to understand that next. So here we are again, back in the rest frame of the platform of observer Om Prakash and his friends. And this is again in Galilean relativity. And we'll assume a simultaneous lightning strike at A and B. And since the clocks on the train are in sync and tick at the same rate as the clocks on the ground, the lightning strike A prime and B prime appear to be simultaneous even to the observers on the train. And now the observers on the train will send out light signals to, the friends A prime and B prime will send out light signals to O prime Prakash. The friends A and B will send light signals to Om Prakash. So A prime and B prime will send signals at the speed of light to O prime Prakash, but crucially they will send out the signals at the speed of light relative to themselves. And similarly, A and B will send light signals to Om Prakash, and they will also send these light signals at the speed of light relative to themselves. So if we play this forward in time, what we would see is that the light beams from A prime and A do not appear to travel at the same rate according to the ground observers. The light signal from A prime, the one traveling towards Om Prakash, has traveled a further distance compared to the light signal from A, because this light signal appears to have, in addition to the speed of light, it also appears to have the relative velocity of the train added to it. Similarly, the light signal sent from B prime towards O prime Prakash has appeared to travel slower. It has covered less distance than the light signal from B. Although it's covered the same distance according to the train observers, according to the ground observers, it has traveled less distance and is traveling more slowly, again because it has the relative speed of the train subtracted from it. So the speed of light is not the same for a light beam sent by the moving observer versus a light beam sent by the ground observer. In other words, the speed of light does not appear to be the same for all inertial observers, in this particular case, observer Om Prakash and his friends. This result would obviously be in conflict with the experimental test of the Michelson-Morley experiment. Now let's review the same incident of two lightning strikes and light signals from the perspective of the observers on the train. So now we're in the reference frame of the train, that is in the reference frame of O prime Prakash and his friends. And here's the platform going by, and the platform will be moving to the left. And what you can see is that all the clocks, again, of the platform observers all appear to be in sync with each other, and they appear to be the same as the clocks on the train. They will also tick at the same rate as the clocks on the train. And now what we see is the lightning strikes A prime, and B prime. And now light signals will be sent from A prime and B prime towards Om Prakash, and these will travel at the speed of light C. And light signals will be sent from A and B towards Om Prakash, and they will also be sent at the speed of light C, but relative to the platform observers. So if we play this forwards in time, what we will see is something like this. Here are the light signals sent from A prime towards O prime Prakash, and these are traveling at a speed C, which in this example is 1 meter per second. So they travel 1 meter, 2 meters in 2 seconds. However, when A emitted the signal, it was here, so this light beam has only traveled a smaller distance as seen by the train observers and appears to be traveling more slowly. This is because it has the relative speed of the platform subtracted from it. Similarly, the light beam from B appears to have a speed greater than the speed of light because it was emitted from here, and it has now has the speed of the platform relative to the train added to it. So these light beams don't keep pace with each other, even though they were emitted at exactly the same time and same place. So light does not always appear to travel at the same speed in Galilean relativity. However, we know that Galilean relativity is wrong because apparently it seems if you want to resolve the null result of the Michelson-Morley experiment, you need to assume that the speed of light is the same as seen by all inertial observers. Now, let's see how it's possible that in special relativity, the speed of light c appears to be the same to all inertial observers. Now, it shouldn't seem surprising given that lengths and times are relative as well as simultaneity, that it can be possible for the speed of light to be the same for all inertial observers. So let's take that same example again with a lightning strike at A and B, which appears to be simultaneous as seen by the ground observer. So now we're in the rest frame of observer Om Prakash and his friends on the platform. And we have this train which is moving to the right. And now as the lightning strikes, A and A prime will both send light signals, A towards Om Prakash, A prime towards O prime Prakash, and similarly B and B prime will send light signals as well. Now, if we play this movie forward, the first thing that we'll see is that the light signals from A and A prime appear to keep pace with each other. And similarly, the light signals from B and B prime appear to keep pace with each other, as seen by the ground observer. In other words, the speed of light c appears to be the same no matter whether the light was emitted by an observer on the moving train or it was emitted by an observer on the ground. As we have also seen, if we play this forward again, these light signals appear to reach O prime at different instants of time as seen by the ground observer. So though the signals from A and B will reach observer Om Prakash simultaneously, the signals from B prime and A prime will not reach O prime Prakash simultaneously. So if we wait longer now, what we will see is that eventually the signal from A prime will reach O prime Prakash. Okay, so those are two distinct events for the train observer. The event of the signal from B prime reaching O prime Prakash and the signal from A prime reaching O prime Prakash. So in other words, the train observers would conclude that the lightning strikes A prime and B prime were not simultaneous, since Om prime Prakash is sitting at the midpoint between A prime and B prime, but he did not receive the signals from A prime and B prime simultaneously, even though they sent him the light signals as soon as lightning struck. So if we look at the clocks of observers A prime and B prime at the instant when lightning strikes, which is t is equal to 0 as seen by the ground observers, we can clearly see this effect. Okay, at the instant lightning strikes, the time at B prime shows -3 seconds, which means all observers on the train agree that at a time of -3 seconds on their synchronized clocks, lightning struck B prime. It was only later that Om prime Prakash came face to face with Om Prakash at a time t prime is equal to 0 according to all the train observers. And it was still later at a time of 3 seconds that A prime came face to face with A and lightning struck them. Okay, so these events occurred non-simultaneously for the train observers. That is, B prime met B first and lightning struck. Then O prime Prakash met Om Prakash, and after that A prime met A. Now let's review this from the perspective of the observers on the train. So for the observers on the train, here's O prime Prakash and his friends. Here's the platform going by, and once again we have length contraction of the observers on the platform, and the actual length between Prime Prakash and his friends is also larger than that apparent 1 meter separation that we saw earlier. And that's because this length would appear to be contracted according to the observers on the ground. So now let's look at the clocks of the ground observers. So if we look at their clocks, so the ground observers' clocks again appear to show this asynchronization, okay, where the clocks over here are behind and the clocks to the right are ahead. So now if we play this movie forward, we saw that at time t is equal to -3 seconds, according to O prime Prakash, his friend B prime so here we see that at a time of -3 seconds, as seen by all the train observers on their synchronized clocks, B prime comes face to face with B. Now, the time on B's clock, as seen by B prime, is still 0 seconds, okay? This is not the same as the time seen on the other ground observers' clocks, all right? In particular, Om Prakash's clock, at this instant of time, if the observer on the train looks out and sees what Om Prakash's clock shows, it would show a time of -2.4 seconds. That is, it has not yet reached a time of 0 seconds. And now lightning strikes at B prime and B. Both B prime and B will send out light signals. B prime will send out a light signal towards O prime Prakash. B will send out a light signal towards Om Prakash. And so if we play this forward in time, what we would see is again these light signals now appearing to keep pace with each other. So both these signals are traveling at the speed of light c, which is 1 meter per second. Again, the thing to keep in mind is that the separation between these observers on the train is actually larger than 1 meter. Okay, and now let's fast forward to the instant where Om Prakash and O prime Prakash come face to face with each other. And here O prime Prakash and Om Prakash have come face to face with each other, which according to the train observers is a later instant of time. This is at t is equal to 0 seconds. And again, according to Om Prakash's clock, you also see that this happens at a time t is equal to 0 seconds. All right. And now if we forward this ahead, we see that at some instant of time, the light signal from B prime has reached observer O prime Prakash. So now they know that lightning has struck B prime. But you see that at this instant of time, lightning has not even struck observer A prime yet. That will happen later at a time of +3 seconds. So if we fast forward ahead, there we go. So observer A prime was struck by lightning at 3 seconds, and now they send a light signal to observer O prime Prakash. And you see that the time at which A prime is struck by lightning corresponds to a time at which A shows the corresponding observer on the ground, A, would show a time of 0 seconds on their clock. And so now, if we watch the light signals from A prime and A, those light signals are traveling to the right and they keep pace with each other. They keep pace with each other, and they are both traveling at a speed of 1 meter per second. Now, so again, the light signals appear to travel at the same speed as seen by observers on the train. Okay, and now something very interesting happens. If you look at a time of 4 seconds on O Prakash's clock, the light signals from A and B have both reached Om Prakash at exactly the same time. So even though the lightning strikes B prime and A prime, or equivalently B and A, as seen by the train observer, are not simultaneous, those signals from B and A reach Om Prakash simultaneously. So O prime Prakash is not surprised that Om Prakash concludes that these signals were simultaneous, or the events of the lightning strikes were simultaneous, even though according to observer O prime Prakash, these events were not simultaneous. So it is only much later that the signal from A prime will reach observer Om Prakash and Om prime Prakash, and Om prime Prakash will know that lightning has struck at A prime as well. Okay, so you see that there's a perfectly reasonable agreement between how O prime Prakash views the world and how Om Prakash views the world. It's just that the dictionary that they use to translate observations between each other is different from the one that we're used to in Galilean relativity. But this dictionary allows for the speed of light to be exactly the same for all inertial observers. The price that we pay for this, however, is that our concept of time being absolute, or the same for all inertial observers, and lengths being absolute are not true. Lengths are relative, time is relative, and simultaneity is relative. So there is one small important point that I would like to make about this particular demonstration. So in this particular demonstration, I deliberately chose the spacing between O prime Prakash and his friends in their rest frame to be larger than 1 meter, and I chose it to be such that when beta is equal to 0.6, the spacing would appear to be exactly 1 meter as seen by the ground observers. So in particular, if I were to take this train to now be at rest, so if I were to slow down the train and stop it here, what we would actually see is that the spacing between O prime Prakash and his friends would be larger than this apparent separation of 1 meter, while the separation between Om Prakash and his friends continues to be 1 meter. So the rest frame length is the true length of the separation between Om prime Prakash and his friends, and similarly, the rest frame length of the separation between Om Prakash and his friends, which here is 1 meter, is the true length of their separation. And the way to really do a comparison would be to compare both of them at rest to each other. So let's summarize what we've learned today. So in today's class, we took a closer look at Lorentz transformations. And we defined a few concepts such as rapidity, boost factor. So rapidity was defined as eta, such that tan hyperbolic eta was v by c, where v was the relative speed between two observers. And the boost factor gamma was 1 over the square root of 1 minus v squared over c squared. And in particular, we saw how this boost factor increases as a function of v. So as v approaches the speed of light, this starts off as 1 for small speeds, but very rapidly approaches large values as you get close to the speed of light. And then we saw that Lorentz transformations actually imply some very strange things that we're not used to from our daily life. And these were phenomena such as the out of phase observations of moving clocks, the relativity of time. Moving clocks appear to tick slower. This is the phenomena of time dilation. And the phenomena of relativity of length. That is, moving rods appear to be shorter, or this is length contraction. And we also saw, using our train demonstration, how the Lorentz transformations are perfectly reciprocal with each other, and how it allows a consistent dictionary of transformation between two different observers in such a way that the speed of light c appears to be the same for all inertial observers. We also saw that in the limit where the speeds are much, much less than the speed of light, we recover Galilean relativity. So in order to have appreciable effects of these new predictions of time dilation, length contraction, and so on, we really need to study observers who are in relative motion with each other with speeds which are approaching the speed of light. This is where we will break from our regular intuition of Galilean relativity, and we will have to develop a new intuition for the world of special relativity.